This is the last question for a paper in summer 2021. This is Cambridge Mechanics 1. So just underlining our aspects of the question here. We have a slide in a playground. There's an angle of 30 degrees and it goes down to the ground for 2.5 meters, and then there's a horizontal section. And we could mention other details there. There's like instantaneous change. Nope. There's a resistance of force. I've just mentioned there, 250 joules. What else? So just taking a question like this, you want to model it and do a sketch at the very beginning. So what I suggest is you do a kind of a top and bottom. Now what I mean by this is actually a kind of a start and finish, initial and final energy or movement sketch. So you want to see basically what's going on. So we have potential energy at the top, as I've written out there, so mgh. And h in this case is not a vertical height, so we've written out a component in its place. So 2.5 is our distance times sine 30. That replaces that. At the bottom of our slope, or the slide, we have a potential energy of 0, and our kinetic energy should exist, of course, because kinetic means movement, motion. So we have half times 35 v squared. Because it's smooth, for now, because it's smooth, it's an equilibrium. So we do not have too many complications. We can actually just say that potential energy, in this case, is equal to the kinetic energy that's been released. So remember what I was saying, initial energy equals final energy. So when you're doing this type of question, there'll be quite a few variations in terms of the formulas and things like this. So you want to just draw it out and make sure it's very clear. So our velocity at the end there was 5 meters per second. The second part, part B, we're trying to find a distance. And the child travels along the horizontal section before coming to rest. Okay. So what's changed here? Well, a change in kinetic energy will be the work done against the resistance. You could also use F equals ma. So you find your acceleration and then use suvat to find the distance. We're going to go the energy route here. So just remember the conservation of energy when you're doing this as well. If it's smooth, like the previous question, like no work took place, but now we have work done against resistance. So we'll make it equal to 250 joules times the distance. And so you'll find the distance from that. Again, you can do initial and final kinetic energy there. We came to rest, so it was a 0 anyway. That's the second part of part A. So we've one more part, part B. It's given instead. So it's given instead is insinuating a change. So we definitely have to draw a new sketch. It's given instead that the sloping section of the slide is rough. Okay, so that's changed. It comes to rest 1.5 meters, 1.05 meters after reaching the horizontal section. Find mu. So your formula F equals mu, or the coefficient of friction between them. Okay, so again, the energy, you want to do the start, finish, or initial, final, whatever way you want to word those things. So your start, you had 0, no kinetic energy, plus 35 g sine 30 times 2.5, which is potential energy. And at the end, we just had our kinetic energy, which was half times 35 times root something or other. So we don't know that yet. We don't know our velocity yet. So we have to kind of redo that bit. So to do a change in kinetic energy, to make it equal to the work done against resistance, we can actually find our velocity that way, just like the previous question, because we have the distance now. We have 1.05 meters as our distance. So having that detail, we can find a difference in the velocity. So I'm going to put that out now. And again, you'll see that I just did my little sketch from the top to bottom, start to finish, initial to final, whatever words you want to use. And 1.05 there is our distance. So from there, velocity, v squared is 15. So v is root 15. So from there, we can put it together. So what is given to us? So we have potential energy. We subtract our kinetic energy. And we also have a work done against friction. So the force, work done is force times distance. Our distance was 2.5 meters. We want to find a max force. And of course, you'd have to think about this and know it from otherwise unit 4, mu mg cosine times your distance is work done against friction. Put that all together. So there's potential energy minus kinetic energy, and we now get our work done against friction. So mu 35 times 10, or 35g if you want, cosine 30 times 2.5. From there you should get that, no problem. Mu is 0.231. And when you're doing just questions, there's variations on what's going to happen here. Like you might want to just in isolation do some work, just looking at how this works. The energy transfer, the force exerted on something. What does it mean? Like cosine means along the direction of motion. You know that from previous units, but you know cosine 90 means 0. So it's up. So there's no energy transfer. There's no work done when you do weightlifting up or something like that. Here I'm just writing the energy initial to the energy of end. You know, these kind of things, you should draw it out. If there's no movement, there's no work done. And you know, your kinetic energy and potential energy, what's happening from a slope, like an incline, when we have one of those questions. An increase in kinetic energy means it's speeding up. A decrease means it's slowing down. If it's equal to 0, that means it's constant speed. So work done equals force times distance. Distance can be height. Force can be mass times acceleration, or mass times gravity, which is weight. It can be lots of different things. The work energy principle, you're going to have to play around with that a little bit. Half times mv squared. There could be 2 kinetic energies, one at the beginning and end, is equal to work done. Work done plus kinetic energy plus gravitational potential energy could equal the final energy of all those. You've got to have a look around and play along with it. The work done by friction, just to look at it in a certain way, it means slowing down the object, the opposite force. So if you're a little bit confused about work done against resistance or work done by resistance, just think about, is it impeding or helping the object on its way? Think of it in those terms maybe, and it could be a lot more clear for you. And that's just a question on work and energy. It needs a little bit of extra work for most people, and try and figure out those bits and pieces and play along with them. Just like science class as opposed to maths class. Look at the real life application of those things, and it'll become a lot more clear to you. And it was question 7 in 2021.